Thank you. All right, so welcome everybody to the third lecture of the tutorial. Welcome to the people online, who are watching us online. This is not online computability, by the way, for those that are watching. I wonder if there's anybody. That was. Okay, so let's start with a quick review of what we did on Tuesday, like a flash review of what we did on Tuesday. We left off at the question of understanding that notion of hyperarithmetic is recursive for equivalence relations. Okay, so while I do the review, stop me if there is any questions or anything. Okay, so those were the topics. We did pi11 sets and hyperarithmetic sets last time, and we got to the middle of hyperarithmetic is recursive section. It's going to be a short section on overspill arguments, which are a very important kind of arguments in this higher recursion theory. They're kind of like the flip side of sigma 1 bounding. We'll see that. And then there's an application of jump hierarchies and overspill arguments to computable structure theory to some result that, at least in the statement, doesn't say anything about higher recursion theory, but that's how we know how to prove it. So this is probably going to be the second lecture today, the second hour. And it includes a proof, but I think it's a nice proof and uses the ideas that we've been developing. So, okay, so ordinals, those are the ordinals. A lot of ordinals. Okay, I'm gonna skip. If I need to review that, then everything's gonna be fast. Pi11 set is one of this form. We talked about that before, and it's being pi11 is equivalent to essentially being able to tell if something is well ordered or not. And the connection is well-founded trees, and you can go from trees to well orderings, from trees to linear orderings in a form that well ordered becomes well-founded and vice versa. Clean you saw. Steve introduced it today. Again, today is the pi11 complete set, and the one I'm using here is a set of indices for computable well orders. So every element of O is assigned a well order. That is the one it's representing. That'll be useful for the way we work with it. Omega 1ck is the least non-computable ordinal which doesn't have a computable representation. And here is sigma 1 bounding, so we're going to use this one. Let me slow down for this one. So if we have a subset of O, so if we have a set of indices of well orders, and the set is sigma 1, then it has to be bounded below some alpha that is strictly below omega 1ck. So some computable alpha that is larger than all these L sub b's. And this is the constructive proof. The other proof, like Liang, you mentioned, is essentially that O itself is not sigma 1. It also works for presentations of well orderings instead of indices for presentations of well orderings. And delta 1 sets are pi11 and sigma 1. Let me go through this very quickly because we can go to this part. Infinitary formulas. I wanted to, okay, let me get to do the part that I wanted to do on pi11's hyperarithmetic sets. Hyperarithmetic sets are definable by computable infinitary formulas, and they are the same as being delta 1, sigma 1, and pi11. And they are all m-reducible to something of this form, all the indices of ordinals below some computable alpha. And that's also equivalent to being m-reducible to 0 to the alpha, like alpha's iterate of the Turing jump for some alpha. And computable infinitary formulas, they have infinitary conjunctions and infinitary disjunctions in the middle. And the computable ones, you need to be able to list in a computable way these disjuncts and conjuncts. Okay, so I could have gave the 2-hour lectures in 5 minutes last time. Oh, and jump hierarchies. I'm going to use this one today too again, so let's review what they were. So if you have a linear ordering L, a jump hierarchy, which is essentially an iteration of the Turing jump along L, is a set of pairs from the linear ordering and the natural numbers. So each column, for each element of the linear ordering, we have the column that corresponds to it, that is a subset of the natural numbers. That one is a jump of all the previous columns altogether. So that's a jump hierarchy on a linear ordering. So one thing we're going to use today, for instance, is that the property, like if you're given H, to tell whether it's a jump hierarchy or not. It's very simple. It's essentially, it's like a Pi2 statement. You have to say for every L and for every N element here, it belongs to it if and only if some computation with this oracle converges or not. So once you have H to decide if H is a jump hierarchy, it's very simple. It's just Pi2. But it expands, it iterates the jump along L. And we said that the Turing degree of the jump hierarchy along an ordinal doesn't depend on the computable presentation of that ordinal. Okay, so that was a very quick summary of sigma 1, pi 1, and delta 1. And then we moved into this property of hyperarithmetic is recursive. I guess I used to use the word recursive when I proved the first the first theorem in 2005. That's why it stayed like that. Okay, so this first result is a classical result of Spector. It's again the sort of saying that how hyperarithmetic sets have these nice closure properties. And it says that if you have a hyperarithmetic presentation of a well ordering, it's isomorphic to one that is computable. And you can prove it using sigma 1 bounding. Okay, so a well ordering, if it has a hyperarithmetic presentation, it's a very large class of sets. Then it also has a computable presentation, which is quite a simple presentation. And then, so this is also true for linear orderings. But instead of isomorphism, you need to use this bi-embeddability property. It's not true for isomorphism of linear orderings. But for bi-embeddability property, if you have a hyperarithmetic linear ordering, it's isomorphic to a computable one. And the proof requires analyzing the structure of the bi-embeddability of the linear orderings and their embeddability and what they look like, and being able to represent each linear ordering that is hyperarithmetic in a computable way, up to bi-embeddability. So the same result is true for abelian torsion groups. Also, it was an easier proof, but it required also understanding the structure of embeddability on these torsion groups and on the pre-groups. I fixed that, Steve. Another example of this property is a counterexamples to Volt conjectures, which we don't know if they exist, but if they existed, this would be another example. It's a funny way of saying it. Another example is a counterexample, which we don't know if it exists. Counterexample to Volt's conjecture is a sentence which we use a theory as a countable list of axioms, which has uncountably many models, but not continuum many models. And if something like that exists, then that's equivalent to having this property of every hyperarithmetic model of T is isomorphic to a computable model. And here is isomorphic again for models for this theory. Okay, so this property kept on showing up. So in 2005, I told you I was already asking, okay, what's going on? It seems like it's quite a weird property because hyperarithmetic is a large class of sets being bi-embeddable with computable. There must be something going on. I had no idea. Then this came around, and I was okay. Well, what's going on? So let's study the question in general. So we say that an equivalence relation E on the reals satisfies this property, hyperarithmetic is recursive, if every hyperarithmetic real is equivalent to a computable one. right? Every hyperarithmetic real is equivalent to a computable one. And that's all these examples on the previous slides are examples of such an equivalence relation. Isomorphism of linear orders by embeddability on these classes. Isomorphisms of counterexamples to Gauss conjecture. And this one too, having the same omega 1, computing the same ordinals, is also an example of satisfying hyperarithmetic is recursive. And one observation is that these are all equivalent. All these equivalence relations are sigma 1, 1. Okay. Let's skip that part. And the question where we left the last time was, so what makes an equivalence relation satisfy hyperarithmetic is recursive? In all those 4 examples, the proofs are completely different looking at the structure of in each particular case. Okay, so at the very end of last lecture, we mentioned that the way the question is stated has the problems that you might change an equivalence relation only on the hyperarithmetic sets, or pretty much on the hyperarithmetic sets, and leave it the same in the rest. And it will satisfy hyperarithmetic is recursive by trivial reasons. And then you won't be able to tell anything about the original equivalence relation. So let me not go through this again, but this will be one way of just changing the equivalence relation on the things that are low for omega 1 and leave it the same in the rest. And this one satisfies hyperarithmetic is recursive, so there is not going to be a nice answer if you're allowing this case. So we need to ask this question on a cone. So let me slow down and tell you, like now starts today's lecture. What do I mean exactly by on a cone? This was mentioned the other day, right? Cone is a set of the form everything above a certain y. I'm going to take the opportunity to draw the Turing degrees, which we all know. We all learned they look like this. And a cone is something that looks like a cone like this. So here is y. All the things that are above y. Okay, so Martin showed that, okay, so here is, I'm only stating this for sigma 1 sets, but it's true for other classes of sets if you use other assumptions. I'm going to use this one in part, so that's the one I'm stating. So if you have a set of reals, subset of the set of reals, that is degree invariant, degree under like Turing degree invariant, so if two things are Turing equivalent, either they're both in or both out, then either the set contains a cone or is disjoint from a cone. Right, so that's essentially what, so Ted mentioned this in his talk, right? So either it's like contains a full cone like this, or it's kind of to the side. But it cannot touch the cone and then not touch the cone. But that's using some large cardinal assumption, not from ZFC, but yeah, not that bad. Okay, so from like, you can use that to kind of define this intuition. So like a measure on the degree invariant sets, and you say that a set like this has measure 1 if it contains a cone and has measure 0 if it's disjoint from a cone. So it's large, you can say a set is large if it contains a cone. Oh. And it's small if it's disjoint from a cone. And that measure is like a sigma additive measure, so it's like an actual measure, a nice measure in that sense. Like a countable union of things of measure 0 is measure 0, countable intersections of things of measure 1 is measure 1. So when I say that an equivalence relation satisfies hyperarithmetic is recursive on a cone, I mean relative to all oracles on a cone. So I mean there exists a y that is the base of the cone, such that for every x above here, the property is true relative to x. Every x hyperarithmetic real is E equivalent to an x computable real. Yeah? So you relativize to almost everybody. So usually when I mean something on a cone means relative to all oracles that belong to some cone, that thing is true. since in computability theory, that's even too little, like almost all proofs, like pretty much all proofs relativize. We know like 4 or 5 that don't, I guess. If E is a natural equivalence relation, like for example the ones in the examples before, you always expect to have that satisfies hyperarithmetic is recursive if and only if it does on a cone. That's, you pretty much expect that's going to happen for a natural equivalence relation. So studying this property on a cone, you don't lose that much because for natural equivalence relation, it's essentially the same as hyperarithmetic is recursive. But you gain in the sense that you're allowed to prove theorems, and you couldn't prove the theorems with this. So you need this notion on a cone to make the theorem true, but morally, it's about the original relation. That's the way I see it. Okay, so we are studying hyperarithmetic is recursive on a cone. So this is a slide from 2012. There was no color by then. 2012, I was after the other Devos conjecture example, counterexample example. I was looking for, okay, what makes an equivalence relation satisfy this property? And like here is like a sufficient condition, and it's, don't even read it, please. But it's like, if the equivalence relation is scattered, projective, ranked, and satisfies blah, 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 then it has hyperarithmetic, then it satisfies hyperarithmetic is computable, and those are the definitions of ranked, scatter, project. It was some condition, which is not, all the examples from before satisfy this condition, so I was, okay, this is a nice condition because it generalizes all the examples. You need to show they are ranked and something, but okay. So it was the first attempt. But here is, well, that's the main theorem from the talk where I copied the slides from. It's not the main theorem for this talk. Okay, so what's the answer? Sigma on 1, an equivalence relation that is sigma on 1. The following are equivalent. It satisfies hyperarithmetic is recursive if and only if it has Aleph-1 many equivalence classes. So it was quite, at the end the solution was quite simple. I mean, at least was simple to state and nice. And it was kind of like right there, because all those examples, they have Aleph-1 many equivalence classes. You have to be, oh, okay, that's what they have in common. Oh, non-trivial, I skipped through that this time. So I said an equivalence relation satisfies this property trivially if every class has a computable member. Like I said, like the Q vector spaces, when there are countably many classes. Like usually, relative to an oracle, if you have countably many classes, they are all computable. So trivially means that's the case. So that's the condition. So that property of hyperarithmetic is recursive is the same as having Aleph-1 many classes. So it applies to all those 5 examples. I don't know if it applies to any other example. So let me see how we're at time. Good. Let me just say a few words about those assumptions. So it needs 0 sharp and not CH, but they are there only to make the statements nicer to state. So the not CH assumption was to be able to, when I say Aleph-1, I don't mean continuum. So Burgess showed that if you have a sigma 1 equivalence relation, then either it has perfectly many classes or at most Aleph-1 many classes. So if it has more than Aleph-1, there has to be a perfect set, so a closed set without isolated points. So like looks like a Cantor set of points all non-equivalent to each other. So it's a perfect set of elements and they are all non-equivalent. So they are perfectly many different, non-equivalent equivalence classes. All right, so if you go beyond aleph 1, you go to perfectly many. So if we want to talk about perfectly many classes instead of continuum, then we can state this theorem without using not ch. And then hyperarithmetic is recursive becomes, it's equivalent to not having perfectly many classes. But if so the not ch was just to be able to state it talking about aleph 1 and to make sure aleph 1 is not the same as continuum. Okay, so not ch was not necessary. Zero sharp. Okay, so there is this definition. So a set is cofinal in the Turing degrees if for every y there exists an x above it that belongs to a set. So it's cofinal in the partial ordering of the Turing degrees. It's equivalent to saying it's not disjoint from any cone. In every cone, there is a member of S in that cone. So Martin's theorem, that the one that we mentioned before, if S is sigma 1, 1, I forgot to say that, and degree invariant and cofinal, it must contain a cone. Because cofinal means you're not disjoint from any cone, so by Martin means you have to contain a cone. So now without zero sharp, you can state the same theorem, but now instead of on a cone, you have to say satisfies this property relative to a cofinal set of oracles. And then that's equivalent to it doesn't have perfectly many equivalence classes. So here is it's even ZF, but ZFC statements. That C is the statement is, I guess, less nice than the other one, but essentially means the same thing. Cool. Okay, so I don't want, maybe I'm just going to say, okay, so let me quickly say, so this zero sharp assumption, so this is a proof in that same paper. Zero sharp assumption it is necessary if you want to state it on a cone. So that property, so the stating on a cone is equivalent to zero sharp exists. And the proof, I'm not going to go through the proof. I'm just going to say that it uses somewhere there bar-wise compactness, which is the next section. So somewhere in the paper is an application of bar-wise compactness. Let me move it very quickly before you guys start reading it. And start with the next topic. Or unless, well, you can ask me later if you want. Okay, so any questions? Not yet, but I guess, I don't know. Oh, there is. Okay, so I put a new version here. Okay, so overspill arguments. So overspill refers to, I guess, in non-standard models of arithmetic, it means that when you have some set that contains like all the natural numbers and is definable, it must overspill and contain some non-standard natural number. In this case, we'll see what it means. It's like an analog version, but in the case of omega 1ck. And ordinals. Okay, so here is the first kind of overspill arguments. So, theorem. There is a computable ill-founded, so not well-ordered, linear ordering, which has, which is a support of some jump hierarchy. So a jump hierarchy, remember, is like you have all these columns, and each one is a jump of all the previous columns along the linear ordering. So we saw before that if you have, for every well ordering, you can define a jump hierarchy because each one is a jump of all the previous ones, so just do it by recursion. So there is some ill-founded linear ordering that satisfies that supports the jump hierarchy. And the proof is very simple. So consider the set of all indices for linear ordering. So E is an index for a linear ordering. over which, or that supports a jump hierarchy. There exists an H, there is a jump hierarchy on L. Being a jump hierarchy, we saw that it was a very simple property because you just have to say that each one is a jump of the previous one, so that's byte 02. So this is a sigma 1 property. There exists an H is and O is a subset of J because whenever we have a well ordering, you can define a jump hierarchy on it by transfinite recursion. But O is not sigma 1. So that means O is strictly included in O, not just included in J. So that means there is something in J. Oh, that's a typo. There is something in J that is not in O. So there is something over which there is a jump hierarchy, but it's not in O, so it's not well ordered. So that's the proof. So these overspill arguments here are kind of the flip side of sigma 1 bounding, because in sigma 1 bounding we define a set, whatever the set is, a set of presentations of well orderings. We say that is sigma. We have to see that it's sigma 1, and we have to see that it's strictly contained in O, and then we know that it's a bound. In this case, we go that O is contained in them, and then since O is not sigma 1, the same reason for sigma 1 bounding, we know that it has to go beyond O and reach some computable linear ordering without descending sequences. Okay, so that's an overspill argument. So here, I guess this is here just because it's an application of this jump hierarchies theorem, and I'm gonna need it for the next slide. This is a theorem of Spector and Gandhi. I don't know what the story is. It was independently proved by them. It says that if you have a set of natural numbers, the following are equivalent. A is definable by a pi11 formula. This is a pi11 formula. Or A is definable by a formula of the form there exists a hyperarithmetic real X such that something hyperarithmetic. So for all X becomes there exists hyperarithmetic, and vice versa. One way, and exists hyperarithmetic becomes pi11. So if you're quantifying over hyperarithmetic reals, the quantifier flips. It's kind of strange. This is not the proof. This is just what you use in the proof for the up to down relation. If you have a pi11 set and you want to write it in this way, what you need to use is that L sub E is well founded if and only if there is a hyperarithmetic jump hierarchy on it. So there are things that are not well founded which have jump hierarchies on them, but they might not be they won't be hyperarithmetic if this is not well founded. So the only things that have hyperarithmetic jump hierarchies are the computable well orders. So that's how you use that part. For the other direction, going up, you just need to show that the set of hyperarithmetic reals is pi11 itself. We'll skip that. Okay, so I'm gonna need that theorem for this theorem. So this one says, this is one of the, this is when the overspill arguments start to become interesting. So there is an ill-founded computable linear ordering that has no hyperarithmetic descending sequences. Okay, so now we have the linear ordering itself is computable, but no descending sequence is even hyperarithmetic. The proof is the same proof that we've been doing so far. Consider all the indices for linear orderings, computable linear orderings, which have no hyperarithmetic descending sequences. So no hyperarithmetic descending sequence is for all hype descending sequence not descending. So this set is sigma 1 by the previous, right? This is for all hype becomes there exists X. Sigma 1, it contains all the well orders, because if you're well ordered, you just have no descending sequence at all, in particular not hyperarithmetic ones. So therefore, O is not sigma 1 itself, so the inclusion must be strict. So okay, I just skipped all the steps here. That means that it has to be something in J that is not in O. But if something is in J, it has no hyperarithmetic descending sequence. If it's not in O, it means it has some descending sequence. But it's not. But they are not hyperarithmetic. Okay. So this one, if you live in the hyperarithmetic world, these guys, they look like well orders because they have no hyperarithmetic descending sequence. So these are results due to Harrison from, I guess, 66. The second result is that whenever you have a linear ordering with that property, it has descending sequences but not hyperarithmetic ones, it must be isomorphic to this. Omega 1ck plus rationally, like densely many copies of omega 1ck. So this means for each rational number, put a copy of omega 1ck inside, plus some ordinal which is below omega 1ck. So it must look like that. And then, like for the case when beta equals 0, that's what is called the Harrison linear ordering. So this linear ordering here, the property is that it has a computable presentation. It's interesting because we said omega 1ck is the first ordinal which has no computable presentation. This one here kind of starts like omega 1ck, but this cut in the middle, this line in the middle that separates this part from this part, is not even sigma on 1. Well, the part on the left is not sigma on 1. Because this part on the left, I mean, it's pi 1, 1, because it's the well-founded part. If it was sigma on 1, it will be delta on 1, and you will be able to get a hyperarithmetic descending sequence on this side. So this cut cannot be delta on 1, because otherwise you get a hyperarithmetic descending sequence on this Q part. So in a sense, this is computable, but the structure is very hidden. It's very hard to understand where the Q is inside this presentation. I mean, it's not hyperarithmetic to understand where the Q is. So it's isomorphic to that, but the isomorphism is far from hyperarithmetic. So the way I like to do both, like sigma bounding arguments and overspill arguments, is instead of looking at all the set of indices for linear orderings, I just fix usually a computable presentation of these guys, and those are my ordinals. And some of them belong to these parts, and those are the ordinals. Some of them belong here, and those are not the good ordinals. They are the non-standard ones. And when you have a sigma 1, 1 set, sigma 1 bounding tells you that if it's included in here, let's do it. Omega 1ck, omega 1ck times q. If it's included in this part, it must be bounded. And overspill tells you that if it contains all of this part, it must overspill, because this cut is not sigma 1, 1. So if you have a sigma 1, it's either included or has to pass the cut, but it can never be there. So that's what both arguments are like. Okay, Harrison linear ordering, super nice linear ordering. Okay, so let's go to Barwell's compactness. I don't know what. Yeah, so the computable, remember this is the LC omega, is the computable infinitary language, where we're allowed to use computable infinitary conjunctions and disjunctions. It doesn't satisfy the compactness that model theory is used all the time with first order logic. A very simple example is this list of axioms up here. If you have a constant C and constants for 0, for 1, for 2, for 3, all these constants, you can write down one sentence that says, for some n, C is equal to n, this junction. And then you can write C is not 0, C is not 1, C is not 2. Whenever you take finitely many of these guys, there is a model for that. Just make C something beyond. but there is no model for all of them together. So it doesn't satisfy compactness, but it satisfies this version of compactness. It's called bar-wise compactness, which is like the omega 1ck version of compactness. So this is kind of following the analogy that Steve was talking about today. When you look at omega 1ck steps. Okay, so I'm going to use omega 1ck to denote that initial segment of the Harrison linear ordering. So here is H. We have a computable presentation of H. So here, when I say omega 1ck, I mean that initial segment of like omega 1ck in this particular presentation. Okay? So suppose we have a sequence index set for E in omega 1ck on this initial segment of computable infinitary sentences. And it's a computable sequence. So we have a computable function f that is given as the indices for these computable infinitary formulas. And suppose that for every alpha strictly below omega 1ck up to here, all these formulas, all these sentences up to alpha have a model. So they are satisfiable. So whenever you take an initial segment, a proper initial segment, you know it's satisfiable, it has a model. Then the conclusion is that the whole set is satisfiable. So it's not true for omega, which that will be like standard compactness will be this same result for omega, but it's true for omega 1ck if you have a computable list of sentences. What's the proof? So consider, now this is the way I like to do this overspill argument. So all the indices in the Harrison linear ordering such that there exists a structure. This is a structure represented, a presentation of a structure such that for every E below that, okay, so I meant J is a set of alpha in H such that for every E below alpha, A models. So alpha could be here or alpha could be there, and it says I have a model of all the previous ones. This set, you might say, is a bit strange because we only have these formulas for E in omega 1ck, and for E beyond omega 1ck, we don't even know what we have. The function might not even converge. But whatever, there is a sigma 1 formula that tells you what this is when you have an E or an alpha in the omega 1ck part. Just use that same formula. Formula says there exists a model, and F converges, and F gives you the index for something, and there is a valuation, true-false valuation that makes it this whatever thing that you get true. So it might not be meaningful when you're talking about when you're in this part, but it's meaningful in this part, and it is a formula in that part. So that formula is sigma 1. It says there exists a model, and a valuation that makes the formula true in the model. Each of those formulas true. And all of omega 1ck is contained in J, but that is our assumption that these guys are all satisfiable. The omega 1ck cat is not sigma 1. Okay, the rest of the argument is the same. So J must overspill. It's sigma 1 and contains this, so it must go further. So we have an alpha like this, which belongs to the non-standard part, because J has to overspill the omega 1ck part. So for this alpha, we know there exists a model A that makes all these formulas true, all the formulas from here to here. In particular, all the standard ones. Yeah? Okay, and the set of these models for this given alpha, the set of these A's that we get is sigma 1, 1, because you had to satisfy all these formulas, a sigma 1 set. So we can get this model to be low for omega 1 by the Gandhi basis theorem that Steve was talking about today. So we can get this structure here to satisfy that for a presentation for that structure which doesn't compute omega 1 ck. That's also part of many applications of barwise compactness use that property right there. Kreisel had a variation of barwise compactness, which sounds pretty interesting. And I guess, well, okay, let me tell you what it is and then comment. So it says the following. So suppose you have a pi 1, 1 set of computable infinitary formulas. And by that I mean a pi 1 set of indices for computable infinitary formulas. And suppose that every hyperarithmetic subset of S is satisfiable, then the whole of S is satisfiable. So it's interesting in the sense that it's kind of like in the standard compactness there is have an infinite set and you have every finite set is satisfiable, and here you have a pi 1, 1 set, and like the hyperarithmetic sets are taking the role of the finite sets. So if the finite sets are satisfiable, then so is S. So in omega 1 ck recursion theory, hyperarithmetic sets are the finite sets in a sense. They are the one you can define below in less than omega 1 ck steps. You can go by both directions. Yeah. So you can go both directions because these guys, well, they are all hyperarithmetic. They are computable, like they're fixed and alpha. These guys, but okay, if you have any hyperarithmetic subset of this set of formulas, it's going to be bounded by sigma 1 bounded, so it's going to be satisfiable. Therefore, the whole thing is satisfiable. That's how you prove this one from that one. And the other direction, like if you want to prove this one from that one, if you have a pi 1 set of formulas, pi 1 is many 1 reducible to O. So you can use that reduction to essentially find a list of your formulas indexed by omega 1 ck. You have to do a little bit of work, but essentially if you have a pi 1 set, you can easily make it into a computable list of formulas up to omega 1 ck. And every hyperarithmetic subset is gonna be containing one of every one of these guys is hyperarithmetic, so they will be satisfiable. So the whole thing is satisfiable. So they're pretty much same thing, both. So what's the story here? I guess barwise compactness refers to a much more general. So this statement is not barwise because he didn't know computable infinitary formulas. They came later from Ash. They use formulas with that can be represented inside some model of KP. And it was more general. It wasn't just omega 1 ck. It was any admissible set. And I guess this formulation is due to Kreisel. Okay, so this is barwise compactness is that theorem that was used in the slides that I didn't let you read before. And it's used for many proofs. So we are going to use it today for the last section of the lectures. Okay, so before we end with this section, I want to mention this other different formulation of overspill arguments. I guess Steve mentioned today that Ted used it. So here's a theorem. There is a model of ZFC whose well-ordered part is omega 1 ck. And it's a countable model. So M is a countable structure with only the in relation. It satisfies all the axioms of ZFC. What M thinks are the natural numbers are the natural numbers. It looks like exactly, the natural numbers in N look exactly like the natural numbers. That's what I mean, omega model. And the ordinals, what omega thinks are the ordinals, they look like the Harrison linear ordering. So what omega M thinks are the ordinals is not really well ordered in the real world, but inside M we cannot find any descending sequence. All these descending sequences that are here, M cannot see them. And the well-ordered part means the well-ordered part of the set of ordinals, which is this part, omega 1 ck. So when I say the well-ordered part is omega 1 ck, I mean that, the well-ordered part of the ordinals is omega 1 ck. In a model like this, what would the computable ordinals be here in a model like this? Well, the computable ordinals will still be computable ordinals here because computability doesn't change inside M because the natural numbers don't change. So arithmetic stays the same. Computable things stay the same. If you're well ordered in the real world, you have no descending sequence, so you're not going to have any descending sequence in M either because M is smaller than the real world. So the well ordering stay the same. So all these ordinals here are still computable well orderings in M, but the computable well orderings are definable within M, and M doesn't see this thing, so it has to be a bit more. So omega 1 ck, according to M, also looks like this. It's not all the ordinals, it's an initial segment of this, but it also looks like the Harrison linear ordering. Okay, so that's what such a model will look like. The ordinals look in this weird way. Yes, I'm using CFC is consistent, but since I believe it's consistent, I didn't add it as an assumption. But yes, it's true. Omega consistent, right. Yeah, you need more than CFC, that's what you mean. Inaccessible, not maybe, I don't know if large cardinal. Yes, you need to show that, so it assumes the existence of an omega model of ZFC. So it's true, this theorem is not provable in ZFC. So for the ones that don't believe ZFC is consistent, you need to add that assumption to make this true. Okay, so what is the proof of this theorem? This one doesn't even need Barwell's compactness, and the proof is very simple. So if you look at the set of countable models of CFC, so they are represented, they are countable structures, which also satisfy that they are omega models. Being an omega model means that you satisfy the sentence. Everything that you believe is in omega is equal to one of the standard natural numbers. So it's just a little infinitary pi 2 sentence. So the set of models of this is sigma 1, 1. You need the sigma 1, 1 because now you're looking at models of an infinitary sentence, not a first order sentence. So we say the model in an infinitary sentence is a sigma 1, 1 property. So the set of models is sigma 1. Therefore, by the Gandhi basis theorem, there is such a model, whose presentation of such a model, which is low for omega 1. So that presentation, omega 1 relative to that presentation, is the same as omega 1 ck. Or in other words, that presentation of M does not compute any presentation of omega 1 ck. So this implies that the well-ordered part of the ordinals cannot be more than omega 1 ck. Because whenever you have an ordinal, something that M believes is an ordinal, M can compute like a linear ordering that consists of all the orderings up to there. So the initial segment up to anything that M is an ordinal is computable from M. And M doesn't compute any copy of omega 1 ck. So everything that M thinks is an ordinal and is an ordinal has to be strictly below omega 1 ck. So the well-ordered part of the ordinals in M can be at most omega 1 ck. But it has to be at least omega 1 ck because we said the computable ordinals, they are still ordinals in M. So all the computable ordinals, because omega is the same, therefore all the computable ordinals have to be actual ordinals in M. So the well-ordered part of M has to be greater than all the computable ordinals. So that means that the well-ordered part of M has to be omega 1 ck. Okay, so when I do these overspill arguments, I usually take presentation of Harrison linear ordering and take the set of all the alphas in the Harrison linear ordering that satisfy some property that is sigma 1. And if you show that it contains all of this, it must go a bit further. And then since you went a bit further to the ill-founded part, some weird things happening, and then you make use of that to prove your theorem. Then, in contrast, we'll start with take an omega model of CFC whose well-ordered part is omega 1 ck. Whatever you are doing, just do it inside this model. Whatever you are doing, if you could show that it was true of all the countable ordinals, in this model, the countable ordinals go beyond omega 1 ck. So take one of these things that the model thinks are well-ordered, but it's not really. And then you get the weird conclusion that you wanted, and then you work with that. So essentially, it's kind of the same kind of arguments, but just a different way of setting it up. And maybe, Steve, you said that for that argument, you actually need to use this method. You mentioned one argument that required something like this. Yeah. It's quite powerful in the sense that it's like pretty much whatever you are doing, you just put it inside this model of CFC. Yeah, and then this model of CFC, as I said before, it's sigma 1, I guess, absolute downwards. So if you have a sigma 1 property about some real here, then that's also true in the real world. Because whatever real was a witness in M, it exists in the real world. And everything that is arithmetic in M is the same as in the real world, because the arithmetic part stays the same. So whatever you're proving, and you end up building something with a sigma 1 property, that was also true in the real universe. Right. Oh, that's why you used it today, right? That's right. Mm-hmm. You could do it, right. All right. So fifth part is going to be an application of overspill arguments and jump hierarchies to build a structure equivalent to its own jump. So I guess I have 5 minutes, so I'll start in the next hour. So we have a half an hour break. Thanks for your attention. Steve?
Obviously, yes, or obviously no.
Okay.
Is the Harrison ordering, if you find it, that's just an order type, but it's computable order type. Is it actually unique of computable isomorphism?
Obviously not. No, sorry, it's not. The answer is no. It's not obvious. It's not obvious. No. No, it's not obvious at all. So, but the answer is no. So, if you have the horizontal a computable presentation like this, and you just truncate it right here, and it still looks like omega 1ck times q, you have another computable presentation of horizontal linear ordering without descending sequences. But they cannot be computably isomorphic, because then you will have to map this thing to this, and then an element here will have to come up here, and then you iterate, and you come up here, and you iterate, and you get a computable descending sequence. So you cannot even get a hyperarithmetic isomorphism between these two guys. Well, I mean, you throw the question like that, so I got to.
So it's not in the world of computable linear order. It's not the Harris order.
That is right. Yeah. So I like to say that, but then it's true that it's definitely not unique, right? And in terms of presentations, it's not.
For just computable isomorphisms, you can use that as really unique specifics.
Okay, to say that it's not computably categorical. Okay. No, but right. So the question is: so it's true that I use it as the horizontal linear ordering, but referring to the isomorphism type. But then when you use it, what you really want is a presentation, and in that case, there is many different presentations.